All right, this takes forever like usual. Okay, so I think it's recording. So let's continue on from lecture 8 and transition into lecture 9, which kind of will cover the topic on virtual memory. Uh, this is an intermediate topic before we learn how the physical memory works. Basically, what happened when you have to access data in DRAM, what happened internally within DRAM. But before we go into that, we need to learn from the program point of view. Let's say you write a program in C, in Python, in Java, and they want to access the data, what actually happened, right? So now that we learn about the memory hierarchy, we learn about the cache, right? The next thing we need to talk about is virtual memory. So before we transition into that, now that we covered caching, the one more thing that we have to talk about is what happened when you have the last level cache miss? Or to be honest, basically what happened when you have a cache miss, right? You have a data request that wants to find the data in the main memory, right? Basically, I have some instruction that wants the data, and the data is not in the cache, it's somewhere in the main memory, right? And DRAM has limited capacity and limited bandwidth, as we all know it, right? When you buy a computer, you can buy a computer with, say, 8 GB of DRAM. You can buy a computer with 16 GB of DRAM. They have this limited capacity. They also have limited bandwidth, right? So if you have basically, if you have heard about this word before, right, you might have noticed bandwidth is a measure of throughput to some extent. Given 1 second, how many things I can do in that 1 second. So that's basically what it means by the bandwidth. But with the notion of bandwidth, it also kind of suggests that, hey, maybe I can do multiple things at once, right? I can do multiple things at once. Let's say I have in the last level cache, right? I have 4 cache misses. Can I basically issue the 4 misses at the same time, right? With the notion of bandwidth, it suggests that that's a yes. And the reason why that's a yes is you have this structure called miss status handling register, or MSHR. So let's say you have a cache miss let's say actually you have a cache miss to 4 cache block, right? Cache block 1, cache block 2, cache block 3, and cache block 4. These are not in the cache at the moment. What would happen is the last level cache, right, basically would issue requests to DRAM all at the same time. All at the same time. But what if there's a subsequent access? Let's say I have future access from CPU 2, right, to cache block 2. And I'm still waiting for my data, right? Do I issue another request to the same cache block 2, to DRAM? The answer is, well, I guess you can do that, but it's not efficient, right? It's not efficient because it's going to waste your bandwidth. You have DRAM bandwidth that is limited, and you have essentially, like, you have the access that wants to access something you already are trying to fetch, right? This is similar to, let's say, I want to go to the cafeteria to get lunch, right? And then I ask my friend, hey, do you want lunch? I can buy something for you, right? So that I will just be the only person who have to go to the cafeteria and get everyone's lunch and then come back and we can take turns, right? So that'd be fair. This is obvious, like, if I ask someone else in the lab and say, hey, do you want lunch? Everyone said no. And every single person has to go to the cafeteria to get lunch and then come back, right? So there are going to be a lot more requests. So when you have cache miss to the same block, the question is, why did you bother sending multiple requests? right, to the same cache block. Because there's already pending, right? There's already pending cache miss that actually generate that data access for you. The better question is how should the cache handle these cache misses, right? So the solution is called miss status handling register. The word register suggests it stores something, right? What does it store? It stores the miss information. So if you want to actually be able to determine, do I need to send the request to DRAM or not? If I have a cache miss, I'll check MSHR and say, are there pending cache miss to the same block, right? So if I have a cache miss, I will check MSHR. And I will wait for pending access. If you already found previous access to the block, right? Then you wait. Otherwise, you issue DRAM access. This is a new cache block that is not in the MSHR. So what is the MSHR? To be honest, this is the high-level overview. About the cache miss, right? You store the miss-related information. These are what is the CPU core that want to access the data so that you can return to the correct CPU. What is the address of the access? Is that a read or is that a write? Why is that the case? So that first of all, you know who wants that piece of data, right? Who demands the data? What else? So that you know all the ongoing misses that are going to be resolved, right? This can be on any cache level. So you can have the MSHR at the earlier level as well. So you know what are the ongoing misses that are going to be resolved. So you don't have to repeat doing the same thing over and over. This is going to eliminate redundant work. Right? So that's the key, eliminate redundant work. And the number MSHR entry, right? This will be one of the limiting factor to what can you have with the in-flight DRAM request. What do I mean by in-flight DRAM requests? These are parallel accesses to DRAM. Why is that the case? If MSHR is full, it means that you're handling, say, 32 or 64 concurrent cache misses, right? There's nothing you can do in the MSHR, so you can, I guess, issue additional access, or you can wait for the MSHR is cleared up, right? So this would be the factor that can impact how the program demand your DRAM bandwidth. All right. So this is basically one additional thing before we transition to virtual memory. And to talk about virtual memory, the first thing we need to talk about is why do we need one, right? Why do we need one? So the answer to that is not that complicated. First of all, as a programmer, you want to have unlimited memory, right? You want to malloc, and never have to worry about your physical DRAM. Is the memory full? If you want to program for the machine that's likely to have multiple other programs running on it, how many times you are running 10 different programs on your computer? All the time, right? All the time. If I look at my computer right now, like my desktop, right? Over here, I have the Google Chrome open. I have Twitch open because I didn't close it earlier. I have Gmail open. I have YouTube open. Well, actually now it's not open. I had it earlier, right? YouTube also would mean you have to have the way to render those video. I also have Microsoft Teams open. At the same time, I'm recording the video. And at the same time, the OS are running a lot of things in the background to make sure everything in your computer run properly, right? So there's so many different programs trying to use your machine. And if you look at the task manager, if you check the task manager, one of the things you might see or observe is these programs use up memory, right? So you want big memory. And at the same time, you want to make sure if somehow my program use say 1 GB of memory, and the other program also use 1 GB of memory, and in total, you ended up using more, right, than what you have on your computer. Let's say your computer has 8 GB in total, but you have 10 programs, each are using 1 GB. In that case, you want to make sure the computer does not crash, because that's bad. You want to make sure somehow your computer still runs, right? So that's why you want to have this notion of you have unlimited memory. You also want to have the virtual view of your own memory. Right? Think about the case where you have 10 applications running, each with its own memory. Nightmare, right? Because programmer should not have to worry about where each of the process memory are. Unless you're working with embedded processors, sometimes you don't have virtual memory and you have you have to explicitly control everything. In that case, it's fine. If you're working with embedded processor or microcontroller that has like a tiny amount of memory, in that case, it might be okay, depending on the ISA specification. You might want to have memory protection. What does it mean? Let's say you run 10 programs in parallel. You want to make sure one app doesn't see the other's application's data, right? Because that's bad. That means that I leak a set of data to some other program, right? But what exactly is a virtual memory? Virtual memory kind of means that every time I need to access a memory, the physical location, which is called the physical address, are not the same as the address that you see on your program, right? Each process, when you're running, the program will see the virtual address. It has its own view of the memory addresses. And the system, the OS and the hardware together would create this mapping between virtual address to the physical address so that you can go to DRAM. So that you can go to DRAM, right? So the first benefit is application would have their own virtual space, right? Each application would have their own virtual space. The virtual address can be contiguous somewhere, this blob that the processor can see and the process can see. And this virtual address can be used for the programmer to basically program in the way they want to without having to worry about some other program that are running. So the second benefit, as I said, you can have unlimited memory. So technically this is limited, but there are ways to create this illusion. Because you know that your computer hard drive is huge, right? These days laptops, you're looking at least 256 gigabytes or more, right? So one thing you can do is you have any data that you rarely use, that data would get kicked out. It get paged out to the hard drive. If you have frequently used data, these data would stay in the main memory. So the benefit, again, the second benefit is this virtual address can be mapped to a much bigger space using the page table structure. And I have a new terminology here, something that's called a page, right? So a page is essentially a range of addresses. In the x86 machine, typically these are 4 kilobytes, but this can be much larger depending on your your architecture, right? Depending on the chip that you're working with, you can have different size for the page table. It's just a range of address that store the address from the address at the beginning of the page to the end of the page. The page table structure is used to determine the physical address given the virtual address. And we apply indirection technique again, right? So page table is kind of like a tree. Think of it this way. You have the root that you can use the virtual address to check the root. The root will tell you, the root will have a multiple branch to the next level. The virtual address that you have here would tell you, right, basically, which branch do you go to? Let's say it's going to this branch. Then this node would have, again, another layer of node connecting to the next level. Which means that you can use it to traverse the node so that you can get your physical page. The page that I talk about. Once you have the page, you can get your physical address because you know what particular address in the page that you're trying to access. So all these page tables are stored in the main memory. So in the Intel x86 processor, you have 4 levels of disk. The root points to the location of the first level. It's just a table, basically. It's just a table. Part of the virtual address will be used to index into the table, and it will go to the next level, next level, next level. You have the example on how this is done in a bit. Virtual address with the data from the first level structure would point to the second level. So each page table, they will store what we call the page table entry. And that behaves like the tag that provide information. And where is the next level of the page table? What's the location of the next level? And it also stores information on, can I access this page? Is this read only? Who owns the page, right? So the page walk process would go through the page table structure so that you can do this thing we call address translation. So when you talk about address translation, let's assume we have 2 levels of the page table. And each page table structure is 1,000 entries. You have 32-bit address. So given these virtual addresses, what are the physical addresses I'm giving to you? And quick note that this 1,000 entry doesn't mean it take 1 kilobytes. It actually generally takes more. It depends on what goes into the page table. And here are the examples of the 32-bit x86 page walk. So if you have a machine that only supports up to 4 gigabytes of memory, this is basically what you're dealing with, 2 levels of the page table. And let's say this is your physical address. This is your, my bad. This is your virtual address. This is your virtual address. What we want to do is, given this virtual address, how do I get the physical address? Right? I want physical address so that I can access my data in DRAM. The way I do this is, first of all, I'll check what's the page size. What's the page size? In this case, it's 4 kilobytes. Right? So I know that the last 4 kilobytes of my address basically would point, like, the last bits of my address would point to one of those bytes inside this 4 kilobyte page. So that particular bit is called page offset. And this is basically sized into the log of page size. Log of page size, so that you can go to each individual addresses, right? So you can go to each individual addresses. Then you're gonna have so and so bits left, right? To basically decrypt your virtual address into the physical address. In the 32-bit x86 page walk, there are two levels of the page table. The first level is called page directory. The second level is called the page table, and the second level would point to the physical page, right? So this is what will happen. You would basically break down the virtual address into multiple sections. The topmost section is used for the first level. So this is typically level 1 index bit. So let's say this level 1 index bit is a bunch of 0 followed by 1, 1. In this case, this number is 3. So what you do is go to the index 3 in your table. You'll be able to find two things. The status, which is, can I access the page? Is this read only? Is it owned by the kernel, or is it the user who owns this page? And then the other part that you're going to find is called page table entry that points to, basically this is a pointer that points to the next page table, the next page table. You would use that because basically this pointer would point to the topmost address of the next level page table. You would then combine with this next set of bits right here. So let's say this next set of bits is a bunch of 0 followed by 1, 0, 0. That number is 4, so it means I'm going to go check the index 4 in this table. This would give me basically your next level page location. And because we only have 2 levels, you know that once you are here, you are basically at the physical page. This is basically physical page number. So to get the physical address, you would append the physical page number with page offset, which is this part here. So you take that, use it as a physical page number. You append the page offset, which you gain from your virtual address. This is coming from virtual address. This part is from your page table. And you put that together, and this is basically your physical address, right? So this whole process might sound complicated, but when you look at each bit by bit, step by step, it makes sense. And it actually just have to follow the steps and you will get your physical address, right? How about what if you have the current machine that you have on, I think, everywhere in the world, right? The 64-bit x86. So the page walk in 64-bit x86 is not that different from the 32-bit version. So in this case, virtual address would spawn, well, you get a virtual address and the address would range from, it would have 48 bits. It will have 48 bits. The last 11 bit is for the offset. Again, there'll be a root that points to the first level of your page table. You then use the index that are from, right? That's from the topmost part to the topmost level, level 4 page table entry. Then you use the level 4 page table entry to point to the next level of my page table so that you can use index number 3 to point to the entry, the corresponding entry. And you can use the entry again to point to the next level of the page table. And you use index 2 to point to the level 2 page table entry, which in this case typically contain the physical frame number. This points to L1 page table, level 1 page table. Again, there's some metadata there, and you can use this to point, right? This thing would point to here and use the index number 1 so that you can get the level 1 page table entry, which contain a physical page number and the permission bits. So once you have the physical page number here, right, and you have the offset here, this is called page offset, this is called PPN. Your physical address is basically PPN, and then you append the page offset. That's all. That's how you can determine where is the address. What is your address, right? And one quick note is everything here is in DRAM. All the table here that you're using are in the main memory. So what it means is that's going to be some performance overhead for sure, right? Because let's say you have 4 levels of the page table and you want to access the DRAM. The problem is basically one data access. You have this virtual address, right? To get the physical address, this means that you go to DRAM 4 times already. Because you have to go to the first table, the second table, then the third table, then the fourth table before you have the physical address. Once you have the physical address, then you go to DRAM. So the problem, first of all, you cannot access DRAM without knowing the physical address. And remember, what did we learn last week? Last week, we talked about caching. So in many modern design, to access the cache, if you don't have the physical address, how are you going to be able to access the cache, right? How are you going to be able to access the cache? The why here is you need PA, the physical address. So let's go through this problem one by one. The first problem is you cannot access DRAM without knowing the physical address. So what could be the solution? We can use the solution we provided for data access. We can use the technique called caching, right? But what do we cache? In this case, to do virtual address to physical address, right? Virtual address has two different pieces of information. You have the virtual page number and the page offset. Physical address also have physical page number and page offset. You notice that the page offset is the same for both virtual address and the physical address. So in this case, if you can cache the virtual page number and provide the mapping that say, okay, if I have this virtual page number, it means the physical page number is this. If I have a different virtual page number, it would map to a different physical page number. Once you have that, you're good, right? So you can use this idea to cache the translation data. So commonly used address, you can put that in the cache. This caching structure is called translation leukocyte buffer, or the TLB. This is one of the most critical structure in your processor to performance, because if you don't have this, translation would be a pain, right? So similar to caching, there can be multiple levels of the TLBs. You can have a smaller private per core TLB and a larger shared L2 TLB. And then if this missed in the cache, you then do a page walk, right? So for the structure of the TLB, think about it as it is going to be similar to the cache, right? Where you can have multiple entry. Inside this entry, if you zoom in, what you're going to have is basically you would have the mapping between the virtual page number to the physical page number. Virtual address come in, you break the virtual address down into virtual page number and the page offset. Use the virtual page number to look up the TLB. Let's say you found it here, right? Then this will basically give you the physical page number. Once you have the physical page number, you just take the page offset, put it here, and this whole thing is your physical address. And this is because this is as fast as accessing a cache, right? So it means that your translation would be much, much, much faster. You don't even have to go to DRAM. Another thing is, what is the size of the page right now? What is the size of a page? Ohad, can you turn on the microphone? What's the size of the page that we assume in x86? It's 4 kilobytes, right? It's 4 kilobytes, which means that each of these entry in the TLB would cover, per entry, would cover 4 kilobytes range of physical address. So let's say you have 512 entry. Let's say you have 512 entry, right? Each entry cover 4 kilobytes. This means that this whole thing, right? This whole thing would cover 2 megabyte region. It covers 2 megabytes only. What does it suggest? Let's say I have a big TLB, like 512 entry TLB. I can only have 2 megabytes of active data. Otherwise, you have to go and do the page walk, right? So there's already been multiple proposals to use what we call huge page, right? Let's say you want to, instead of storing 4 kilobytes of physical page information per TLB entry, and that's somewhat small. The coverage we have is 512 entries. It's only 2 megabytes. So the TLB can cover only 2 megabytes. One possible solution, this is actually available in Linux. It's called Linux THP. Is called huge page. So with huge page, you will use the physical frame number. If you remember, go back to the example from the 4-level translation. Level 2, right before you go to level 1, what you get is the physical frame number. So we can use this physical frame number with longer page offset, which means that you can operate at 2 megabyte page, which means that you can operate at 2 megabyte page. And this page size, right, can be adjusted based on the ISA and the OS. For example, each GPU would have its own page size depending on the size of the GPU's memory and the number of the TLB entry. Many design on the GPU is geared so that the whole TLB would cover the GPU's memory, and that's it, because it means that everything would hit in the TLB, right? So this huge page sounds nice, right? This huge page sounds nice. The problem with huge page is this. When you have the better, larger TLB reach, the problem is you have, first of all, you have this problem called fragmentation. Sometimes you allocate data for only 10 bytes, 40 bytes, 1 kilobyte, right? So when you have to allocate this small data, but you want to use huge page, you can have fragmentation problem. On the plot I'm showing here, the y-axis, and this plot is from one of the paper called InGen, presented at OSDI. OSDI is a top, like the world best conference for computer system. On the y-axis here, you see the fragmentation index. The x-axis is time. What you're going to see from this plot is it basically, the experiment run Redis. Redis is one of the common workload that in theory, it should benefit from using huge page. But the fragmentation index, which is how often do we have holes in your huge page, and you ended up underutilizing your DRAM capacity. Let's say your DRAM has 16 gigabytes. When you turn on huge page, you effectively only get about maybe 12 gigabytes or 10 gigabytes. So you can see that when you have huge page turned on, right, fragmentation index go way up to the point that at some point it's not useful. There's also another problem that's basically when you have a page replacement, when you want to kick something out of your DRAM, but if you have huge page, you will have this dirty data amplification, which means that I only modify, say, 10 bytes of the whole 2 megabyte page, right? So I have 2 megabyte page. This data get modified. And because of that, it marked the entire thing. It marked the entire thing as dirty, which means that you have to basically, to do the page replacement, you have to make sure you commit this dirty data. The problem with huge page is the dirty page amplification is really high, really high. So this is data from the HotOS 2019 called the Project Peaberry. This is a project in collaboration with the student at Zurich and VMware. The last problem is you're going to have the problem with promotion and demotion. So this data going back to the OSDI paper, it runs 3 virtual machines. On the y-axis, you see the huge page consumption in megabytes. So you want them to be as big as possible. The more you can have, the more huge page you can basically run on each machine. But you can see from the plot, right? It's clear that VM3 got out a huge page, while VM1 only have certain amount of huge page, and that's all. VM2 never got one. So promotion and demotion is also a problem. Why are the problem happening? The problem happened because you have this thing called fidelity loss from using huge page, right? So if you remember this, we covered this in our workshop from last Monday. Yeah, the Monday last week, right? When I talk about my work called Prism, which basically addressed this problem. But the fidelity loss in 2 megabyte page is something like this. This is similar to, let's say I'm running a building, right? I need to maintain the building. This is a picture of the Willis Tower in Chicago. If I operate using a small page and say, hey, I have a dirty Windows. So I would basically tell the maintenance crew, right, to say, hey, the window pane is dirty. We need to clean it, right? So, well, I'll go and clean that because I know exactly where that window is because I'm running small page. But let's say I change the page granularity to a huge page from 4 kilobytes to 2 megabytes. In that case, you don't have each window's information. You have the whole side of the building's information. So with large page, when the windows is dirty again, right? What you see is like that whole side of the building is dirty. I don't know which window is dirty. The only thing I can do, I'm gonna clean this whole side of the building. So if I have to clean this whole side of the building, it's gonna be a lot more work. It's gonna require a lot more work, right? So that's basically the fidelity loss problem. And the main problem that comes from it is because the information about huge page is tied to the page size. What we did in our work in Prism is basically decoupling that, making sure page information is not tied to the page size anymore, right? Okay, now we cover how we can use the translation leukocyte buffer to address the basically the translation problem. The second solution, again, caching, right? So you can see how powerful this concept of caching is. You have a fast memory, you have a slow memory. You want to use the fast memory to cache things for the slow memory. We can do that again, but instead of basically what you have in the TLB, right? TLB, you skip from virtual address, skip to physical address right away, right? With no TLB, you would start from virtual memory. You do page table level 4. Then page table level 3, then page table level 2, then page table level 1. Then you have the physical address. So one thing you can do is instead of skipping the whole way, and to be honest, sometimes you miss, right? You miss because you need to make sure the whole virtual page number match. Why can't we have this kind of like a fast track? We would cache this portion. So when you have the virtual address, it go to physical page table level 2, and so they can do level 2, level 1, and physical address. This is called the page walk cache. It caches partial translation data so that when you have each page table structure, you would store the common page table location. This common page table location is called the page walk cache, and the benefit is it's gonna provide much higher coverage than just the TLB. And you can cache partial translation data. What are the downsides? Downside is you still have to do some translation. So you still have to do some limited amount of translation. And what you see so far is you see that, okay, page walk is really expensive. So we want to avoid, right? We want to avoid as much page walks as possible. And to do this, you can use a combination of multiple solutions. You can use the TLB. You can use the page walk cache. You can even use a data cache to cache the translation data. And there are also many other ideas on how to reduce the page walk. For example, you can use large page. You can use segmentation. You can reduce the complexity of the TLB. You can use a different page table structure. And there's an idea called elastic cuckoo page table. This is out in 2019 in one of the major conferences. This is also another really interesting idea. Wait, is it 2019 or 2020? Let me double check. Oh, 2020 in March. Basically, this is 2020. My bad. I'm sorry. Forgot about the year. I thought it was 2019. So this is an idea in AFOS 2020 that basically talk about, okay, if we don't use this radix space tree for your page table, you can use a different technique to kind of rethink how virtual memory and page walk should be done. Okay. There's also some work on GPU side optimization as well. They're quite well, to be honest, I personally work on this. I have a paper again presented already to some of you, to both of you. Actually, you've seen this before. One published in 2017. The other one is 2018. There's also I think 3 or 4 other research group that works on this. If you're interested in more detail about that, if you have follow-up question now that you learned virtual memory, and you've seen my talk from last Monday, feel free to let me know. And that's kind of covered the first part. You cannot access DRAM without knowing the physical address. Now let's do a quick 10 minutes break. Let's do a quick 10 minutes break before we dive into the second problem that can happen, right? So I'm gonna basically do let's do 12 minutes break. We'll resume at 10:10. We'll resume at 10:10. I think I cannot stop the recording, so just keep the recording going. I'll mute it myself, and we will be back at 10:10. All right, and when we come back, we'll talk about what would happen. You have to access the cache. Okay. All right. Are we back? Oh, Pat, you're back. Thank you. You're fast. Okay. So let's resume the discussion a little bit. You still see my screen, right? Okay, awesome. So let's resume the discussion now that we talk about, hey, if I want to access my data, I have to do multiple trips to DRAM just to know the address, which means that one access would be overblown into multiple other accesses. And we talk about how to address that problem using a TLB and a page walk cache and huge page and many other techniques. If you're curious about that, check our reading list from the virtual memory part. I'm going to update that list a little bit to kind of reflect newer techniques that work for virtual memory and kind of like the paper that came out from these last 2 years as well. There are quite a few interesting papers on this topic. The second problem is, in many modern design, you cannot really access the cache without knowing the physical address, right? If you talk about the cache, there are two main things that's basically inside the address of the cache access. The first thing is the index bit. The second thing is the tag bits, right? These are used to index into the cache and so that we can pick the set that we want, or to figure out, is that my cache or is it someone else's data, right? So to figure it out, it means that you can have either virtual address or the physical address for the index bit or the tag bits. So index bits can come from virtual address or physical address. Same goes for the tag bits. It can be from virtual address or physical address. You have 4 choices in total if you combine all the options here. You can have PIPT, physical address for all, right? Physical address for all. You can have PIVT, use the physical address for index, virtual address for the tag. You can use VIPT, virtual address for the index, physical address for the tag. And you can use VIVT, virtual address for the index and virtual address for the tag. If you look at these 4 options and think about when you have multiple applications running, like in the case of having multiple applications running, you can run into a few problems. The first problem is called homonym problem. 2 programs running happily ever after, and then they happen to have the same virtual address. They happen to have the same virtual address. But because there are 2 programs, it maps to a different location. Virtual address that are the same, A, right? This is program 1, program 2. When you do translation, this go to physical address 1 and this go to physical address 2. 2 different physical address. But it happened to just be the same virtual address because the virtual address, what the OS give you? Hey, use this address. I can do the translation. I'm fine. I can do the translation the way I want it to. It just happened to map to the 2 different virtual address. So it means that if you look up the cache and use the virtual address for the tag, you might have the problem because you might not see your data, but you see someone else's data. It's called homonym problem. The tag need to be able to tell the difference between the 2 pieces of data. Otherwise, you better fetch the wrong data. You also have this synonym problem where 2 virtual address can be mapped to the same physical address. Can be mapped to the same physical address, right? You can have this when you have, for example, shared data. And this is called synonym problem. So the tag need to be able to tell the difference between the 2, right? Otherwise, well, you're still not fetching the wrong data, right? You're not fetching the wrong data because it's the same virtual address. So there's no problem here, right? There's no problem here in terms of using the tag because you have 2 virtual address 1 and virtual address 2. It's going to spawn basically tag number 1 and tag number 2, right? So if you ask, like, is this going to be wrong? It's not really the case. It's not going to be wrong, right? You have two tags. But the homonym problem where you have one virtual address mapped to two different physical addresses, one for program number 1, the other one is for program number 2, can basically give the answer to this question. Should the index be from the virtual address or the physical address? And should the tag be from virtual address or physical address? We just talk about the tag, right? Out of these 4, PIPT, PIVT, VIPT, and VIVT, the homonym problem has to do with the tag. And to summarize, right, if the tag use virtual address, you have the problem. Because sometimes you have the same virtual address, which means you're going to have the same tag, but it goes to a different physical address, so you got 2 different pieces of data. So what you want is to use a physical address for the tag. Otherwise, these 2 options would lead to homonym. There are some proposals that say, hey, with large memory, there's no need for the OS to have the same virtual address because you have a much larger space for your virtual address. So VIVT is fine, but we're not going to talk about that for now. If you're not going to talk about that for now, if you're curious, again, check our reading list. There's also papers that would cover this discussion, right? But if you can use VIVT, you don't have to worry about translation at all when you want to access data in the cache. So VIVT is really fast for sure. Why are they fast? Because it does not need to do translation to access the cache. But it's going to run into homonym problem. So we only have the limit between PIPT and VIPT. The issue with the PIPT is you need to first, the first thing you have to do is to get the physical address before you can do anything with the cache, right? You need to translate the virtual address before you index and before you look up in the tag. This is gonna sequentialize the process. You have virtual address, you do translation. This alone is either one additional TLB access or 4 DRAM access. Then you have the physical address, then you do the cache lookup. Right? So in this case, at minimum, the lookup has to be done after the TLB accesses. So this is going to be slower. It is going to be slower. So you want to avoid using the physical address as much as possible. So the other end of the spectrum is, well, why can't we use VIVT? You can perform cache lookup without the address. But you can possibly run into a homonym. So what do we do? There are, again, there's quite actually a good body of work that kind of vouch for VIVT and make sure we don't have homonym problem in the first place. Make sure the OS never assign the same virtual address for different program, right? And this actually, to be honest, I kind of like this proposal as well because this would get rid of the homonym problem and you get the best of both worlds. Right. So, for example, this paper from ASPLOS 2018 kind of talk about this and propose a design that discuss this quite a bit. What about VIPT? VIPT means that I have a cache lookup, right? But I use the virtual address for the index bit and use the physical address for the tag bit. Why is this okay? because we use physical address for the tag bit, again, the question, why is it okay? Because tag is used to check if this is your data or not. Because if you think about it, the index bit is used to get the set ID. So if you have the homonym problem, same virtual address mapped to the same that go to different physical address, well, I would go to the same set regardless. That's okay. Because I'm going to use the physical address to check if that's my data. So that's going to be totally okay. The benefit of VIPT is you can overlap, right? You can overlap the cache lookup, the lookup latency with the TLB lookup. And you can still use the physical address for tag checking. So it will get rid of homonym problem. Get rid of homonym problem. What's the downside? If you have a TLB miss, you still have to do the page walk before you can access the cache. Before you can access the cache. All right, so that's gonna cover the link between caching and address translation. If I need to access my data in the cache, I need both the virtual address and the physical address. I can use the virtual address right away from my processor to go index into the cache, and I would use the physical address as a tag bits. What about page fault? What about page fault? Virtual address also provide a virtually much larger memory than DRAM, right? So pages that are not used there are stored in the storage, like hard drive or SSD, right? So what if you want to access pages that are not in DRAM? This is called a page fault. So basically you will go walk the page table and the page table tell you, hey, it's not in DRAM. Go look up your hard drive. It's the page fault process. So the remedy is you're going to retrieve the page from the storage. So this process takes a really, really, really long time. Typically, that's when your computer would slow to a crawl, right? So you have a program that are running together. Let's say you have a Chrome that have 100 tabs opening. You're likely to have a bunch of page fault because each tab would use some memory. Each tab use some memory from your machine. So you ended up having to go to this much slower hard drive or SSD quite a lot. Another thing is with VIPT, you can still have synonym, right? Synonym is when you have two virtual address mapped to one physical address. Solution with synonym is you can, well, limit the cache size, right? So that the cache index is from the page offset. Why is that the case? Why is that good? When cache index is from the page offset, this means that both virtual address and physical address has page offset. So this is one possible location. The other possible thing you can do is to search all possible indices that can contain your physical block, or you can do page coloring. If you do page coloring, it basically means that I'm going to restrict by the OS where page of each process can go. This would ensure that the index, right, your index for your virtual address would go to the index of the physical address. Because otherwise you have two VA, right? This is going to give two set of two index bit. Index 1 and index 2. But when you have two index bits and you have the same physical address, it's kind of annoying because you're basically wasting two cache blocks, right? And the other thing is memory protection with virtual address, which is our third benefit. And this part can be easily explained because now that we have the page table structure, right? You have the page table structure. When you do the page walk, Address translation can be utilized when you do page walk to check if my access is valid or not. How do we do this? Our page table entry would contain permission bits. This bit would check on each access if there's any violation, and the bits can include this thing called address space ID, which basically tells is that the data that you own or is that someone else's data completely. Read and write versus read-only bits. User versus supervisor bits, right? User versus supervisor bits. Am I in a user space or in a kernel space, etc., etc. So let's put everything together. Let's say you have a pointer in your C program, something like this. Int star I equal, and then I say I star I equal 10. Right? What happened to the pointer when you access? Let's assume you do malloc properly, right? What happened when you do star I equals 10 when you want to access the data? And I'm going to use this particular high level figure to show you a day in life of my data access, right? I have the processor to the left. I have DRAM to the right. In the middle is still is everything inside your CPU that you buy, but it's not the compute part. It's all the caching structure on the top and all the translation structure on the bottom. For all the caching structure, you can have the L1, L2, and L3 cache. The translation structure, you can have the TLB, right? And you have the MMU that performs the page walk. This would go to the DRAM multiple times. And you have the load address. This is basically when you do star I equals 10, right? This is, well, star I equals 10 at the store. But let's say you want to print star I. What's the value at address I? The first thing you do is this is virtual address, right? This is basically virtual address. So the first thing would happen is the index bit, from the virtual address would go to the cache. Then the virtual page number, again from the virtual address. Virtual address basic would consist of virtual page number and the page offset. So the virtual page number would go and check the TLB. If that's the hit, you get the tag. Because if that's a hit, you basically get the physical page number, which means you can combine that with the page offset to get the physical address. Now that you have the physical address, you can use it as the tag bits, right? That would get rid of the homonym problem, and you can have a happy life, check the L2 cache, check the L3 cache, or go to DRAM if needed. Otherwise, if you missed in the TLB, you would then check with the page table, do the translation by accessing the page table multiple times in order to get this tag bit, to get the physical address, in order for you to look up the cache. And then you check the cache. If it's a miss, you go to L2. If it's a miss, go to a last level cache. If it's a miss again, you use the physical address to access your data, right? To access your data. And the physical address is basically physical page number appending with the page offset. All right, so this is basically what will happen when you have data access. So let's look at modern day workload, right? What are the hot topic nowadays? Machine learning, AI, whatever we call big data nowadays, because data is always big. I don't even know why we call big data, because it's always much, much, much bigger than what you can have on one machine. So by default, it's big. Everything you have to do in a realistic scenario is big data. Even back in like 1960, it's just a keyword that business people throw out, to be honest, which is kind of stupid. When you have these large amount of data that you have to train from machine learning workload, or a huge data set from the AI workload, a huge model that you have to do, or things like IoT, which in that case, you have a small device. So your data is going to be sometimes bigger than what you can maintain, right? In these cases, everything involves virtual memory. Because every single piece of the program would go and access a bunch of data, right? Lots of data access. Lots of data access. So the goal, if you want to optimize, you want to minimize the data miss in the cache, right? The cache and the TLB. Basically, you want to make sure you have the locality that you can have and make sure your code is optimized for locality in both the caching structure and the TLB. Most of the time, if you do it for the cache, it would have a really good locality on the TLB as well, because TLB is bigger than the cache, right? And many high performance computing workloads I've seen from, at least in the United States and in the competent lab, right? They would try their best to make sure this happen. I still see a lot of a huge gap in these kind of style of programming in Thailand. Like, people here just say, hey, I just want to implement this feature. Once I have the features done, yay, I'm done. But they never realize that the things they develop are going to be really slow, right? So you're gonna end up with a lot of apps that are slow, a lot of accesses that are, well, I mean, slower than they need to be, right? Slower than they need to be somehow, right? And I can give you so many examples of like website that internally somehow is really slow. I don't know who developed this, but it's basically not according to a typical guideline on how you develop this kind of website, like a shopping website, or the websites that have to maintain large database. This is a big problem. In a virtual machine is also a big problem with VM. So what is a virtual machine? Basically, this is basically a machine in a machine, right? You have the OS running inside the hypervisor that run another OS. That's why we call this virtual machine. Or you can have container. Again, I talked about this already in a workshop last week, but containers are essentially, now you can share the OS, right? Now you can share the OS, but things in a container that are running would be like a separate entity. So you can spawn, right? So you can spawn tasks that would maintain the database, and you can run it in a container. Docker, right, for example, is one example of a container. And in the world of big data, what if you have a lot of data access, like huge graph or huge data in ML training? What happened is address translation is a big problem. Why is that the case? Why is VM in the cloud has a big problem with address translation? So you can have the guest, right? OS. This is where your program is running. And you have the host OS. Basically, this hosts all the VMs. And you have DRAM right here. What you're going to have is, when you have pointer access, again, star I, right? I have guest virtual address, which means that I would have to do translation inside the guest OS, right? So I have guest page table 1, page table level 4, guest page table level 3, guest page table level 2, guest page table level 1, and guest physical address. Everything here in the guest OS is the virtual address in the host. So guest page table level 4, this is basically virtual address on host. So you have guest level 4, guest level 3, guest level 2, guest level 1. and then guest physical address, right? Which kind of means that every time you have the guest page table access for DRAM access, for DRAM access, for, and for, right? So this is already 20, right? This is already 20 accesses. Just to get the physical address of each one of them. So this part is 20. And then you have the physical access again, this is 4. So in total, one guest virtual address into one host physical address contain 24 accesses. That's quite a lot, 6 times higher, right? So that's part of the reason why when you use a virtual machine, this can be really slow, right? And there are many works that kind of would try to reduce this overhead. Again, the reading list would have that. If you're curious, feel free to check the reading list and check with me, and I can kind of guide you through this, because again, this is a topic that's close to myself, right? Close to home, because I work on this a lot, and I kind of want to share what are the awesome work that people in the world have been working on. There are multiple labs working on these problems, and I think it's one of the big problem in architecture, because we have to figure out, okay, when we have serverless, when we have container, when we have VMs, right? How are we going to address this problem? What if you want to connect multiple machines together? All right. So that's it for the lecture today. I have a phone. Let me pick up this call quickly. I'll be right back.
Professor, can I ask some question?
Okay, so first of all, let me stop the recording because that's the lecture part. All right, so